Hi guys, welcome to the third video of machine learning. Now, one of the most important part of machine learning is training models. So let's learn about it today. In this video, we will learn about linear regression, gradient descent, polynomial regression, and logistic regression. Now, we will start by looking at the linear regression model. It is one of the simplest model out there. Now, what is linear regression? Linear regression is used to predict the value of a dependent variable based on the value of an independent variable. In this case, we want to predict the weight based on the length. Now, by using data to train the linear model, we get an equation. If you remember, y equals to mx plus c. That's the equation for linear model. And in this diagram, the model equation is weight equals to negative 11.03 plus 2.21 times length. So this equation forms the dotted line. So when we have new data on the length, we can easily predict the weight using this model equation. And that is the simplest type of training model, linear regression. For linear regression, there are two very different ways to train it, using a direct closed-form equation that directly computes the model parameters that best fit the model to the training set. Or we can use an iterative optimization approach called gradient descent, and that gradually tweaks the model parameters to minimize the cost function over the training set, eventually converging to the same set of parameters as the first method. We will look at a few variants of gradient descent that we will use again and again when we study neural network. So there'll be batch gradient descent, mini batch gradient descent, and stochastic gradient descent. Now here's an example diagram of gradient descent. Gradient descent is a very generic optimization algorithm capable of finding optimal solutions to a wide range of problems. The general idea of gradient descent is to tweak parameters iteratively in order to minimize a cost function. Now there are three types of gradient descent: batch gradient descent, stochastic gradient descent, and mini batch gradient descent. Batch gradient descent uses the whole training set to compute the gradients at every step, which makes it very slow when the training set is large. Now, stochastic gradient descent just picks a random instance in the training set at every step and computes the gradients based only on that single instance. Obviously, this makes the algorithm much faster since it has very little data to manipulate at every iteration. It also makes it possible to train on huge data sets. Mini batch gradient descent computes the gradient on small random sets of instances called mini batches. The main advantage of mini batch gradient descent over stochastic gradient descent is that you can get a performance boost from hardware optimization of matrix operations, especially when using GPUs. The diagram shows the paths taken by the three gradient algorithms in parameter space during training. They all ended up near the minimum, but batch gradient descent path actually stopped at the minimum, while both stochastic gradient descent and mini batch gradient descent continues to walk around. However, don't forget that batch gradient descent takes a lot of time to take each step, and stochastic gradient descent and mini batch gradient descent would also reach the minimum if you use a good learning schedule. Now, what if your data is actually more complex than a simple straight line? Surprisingly, you can actually use a linear model to fit nonlinear data. A simple way to do this is to add powers of each feature as new features, then train a linear model on this extended set of features. This technique is called polynomial regression. It is a more complex model that can fit nonlinear datasets. Since this model has more parameters than linear regression, it is more prone to overfitting the training data. Now, the green line is the high degree polynomial regression model. It is severely overfitting the training data. As you can see, that it's overfitted, while the linear model, red line, is underfitting it. The model that will generalize best in this case is the quadratic model, which is the blue line. Let's look at how to detect underfitting and overfitting using learning curves. The left diagram is a learning curve of an underfitting model. Both curves have reached a plateau. They are close and with fairly high errors, RMSE. While the right diagram is a learning curve of an overfitting model. There is a gap between the curves. This means that the model performs significantly better on the training data, which is the red line, than the validation data, which is the blue line, which is a hallmark of an overfitting model. However, if you use a much larger training set, the two curves would continue to get closer. But we can't solve underfitting model with more training data. It needs a more complex model or a better features or X or independent variable. Next, let's look at logistic regression. Now, both linear and logistic regression are among the most popular models within data science. Linear regression models are used to identify relationships between a continuous variable and one or more independent variables. When there's only one independent variable and one dependent variable, it is known as a simple linear regression. But as the number of independent variable increases, it is referred to as multiple linear regression. For each type of linear regression, it seeks to plot a line of best fit through a set of data points, which is typically calculated using the least squares method. Similar to linear regression, logistic regression is also used to estimate the relationship between a dependent variable and one or more independent variables, but it is used to make a prediction about a categorical variable versus a continuous one, like what the linear regression use. So it is mostly used for classification tasks. Now, a categorical variable can be true or false, yes or no, 1 or 0, etc. The unit of measure also differs from linear regression as it produces a probability, but the logic function transforms the S-curve into a straight line. So that's all for today's video. If you are interested in this slide and the content of this video, please go to the innovatorsdigest.wordpress.com to download them. Thank you so much for watching. I'll see you in the next video.